Can you see my screen?
Yes.
Okay, thank you. So this part will look a little bit more about projects, and we will then look at our systems and the file system, and which is very important, the module system, and then a little bit about compiling and linking, and then much more about the batch system, and there will be some examples, and you will get to do some exercises. So, but let's get started. So it's only half an hour before lunch. So right now you're all in the course project, but after that runs out, that will be active until around the 1st October. Then you will need your own project or to be part of a project in order to continue working at SPC2N. And as I said, Kebnekaise is only open to local projects. That is people at Umeå, Luleå, IRF, Mid-University, or SLU, or someone who has a PI at one of those places. Because that is what matters. It is where the PI is located. Where that person chooses to add users from doesn't matter. They can be in China or whatever. That is not a problem. It is only the PI that needs to be affiliated with these universities. So if you are the PI, you need to be that. So to apply for the compute projects, you do so in Super. And you go to this link here. And at that link, well, you log into Super and you click rounds and go here, go directly to the link. And if you want a local project, then you pick compute rounds and then center local compute and pick HPC2N local compute, and then it will be whatever year it is here. And there are also other systems that you could choose, and those would be on a small, medium, or large instead of local compute. And if you need a larger project than the one you can run here, then you can pick that. But right now we're going to look at the local projects. And if you don't have a project before, then you would create from scratch. Otherwise, you can use an earlier proposal as a starting point, and that means simply copies the data from previous project, and then you can make changes to that, and that is often much easier. And you can then choose to agree to the default storage if you think 500 GB is enough, or otherwise you apply for a storage project, or in this case, a local storage project. And there will be more information about all this on the Super system. So, as I mentioned, you have 25 GB in your home directory. And in this case, in the course project, we have 500 GB shared in this area here. So under that, you create your own directory. And if you had created a storage project also, then you would link them together with the compute project. And then anyone who is part of the compute project would also be part of the storage project. And I had a short text about that, but I'm going to jump past that because we are short on time, and you can read it later yourself if you want to. It is not important unless you need a storage project to a compute project you have created. And it shows you how to go in there and find the project that you want to link and how to do that. So let us look at the systems here in general instead. So you're connecting to Kebnekaise, and this is the exercise you just did, and that I hope worked for you. and you log into this link to this login node here, this server. And the other option was the web access, which has less features. It's slightly difficult to copy things, but otherwise it has most. Or if you already had an SSH client you liked, you just use this login node instead, kebnekaise.hpc2n.umu.se. So you can see the difference is that there's a -TL at the end of Kebnekaise for the thin link one. There is also the possibility of logging into a specific login node if you are using the new A100 ones. And the reason for that is that they are running a newer version of Ubuntu. They are running 22.04. And they are also having newer versions of CUDA and things like this. And that means that there is different modules there, and there is different compilers, so you need to log in there if you want to submit anything to that. But we're not doing that right now. So use this for thin link and this for regular SSH. And then you would transfer your files and data if you had any you wanted to do that with. You would load modules if you, for instance, need to access some software, or if you need to use a compiler. If it's your own code, you would probably compile it, or you might also have software you want to install, or you have pre-installed software you want to run. And after you've done that, you would create a batch script and you would submit a batch job. And then at the end, you download data or results to some local or other machine. And that is, of course, optional, but that is if you need to do any post-processing or whatever. So this is the usual walkthrough. This is a walkthrough of the usual workflow you would have. And I have already mentioned this. And if you need to transfer files, Pedro already talked about this, but you would use this if you're on Linux, and if you're on Windows, you would need a client. You would, for instance, use WinSCP or FileZilla, and we have more documentation about how to do that. And there is documentation here in general for how to do it. But if it's from Mac, you can do it the same way as on Linux. And this, again, is something that Pedro has talked about, how you edit your files. It is probably somewhat different to what you would use if you're used to Windows, also if you're used to Mac. There are some editors already installed on the system, and as Pedro mentioned, it's probably easiest to use Nano if you haven't used any of them before. If you're using it remotely without having a graphical interface, Nano or Vim is probably the easiest. If you're also logged in to a graphical interface, then Emacs also is a good way to run it, but probably Nano for now. And there is a slide here that shows briefly how you would use it. So you start Nano with Nano file name and press enter. If it's a file name that exists, it opens. Otherwise, it creates this file. And at the bottom, you would see many of the commands. And if there is this hat thing here before a letter, it means you should press Control and that letter. And to exit, you press Control and X. That it means you press Control and hold it down while you press X. And then it will ask you if you want to save it or if you just want to exit it. So there are some file systems on Kebnekaise. There's the project storage, and here we can say that if it's recommended for batch jobs, yes, you should do that in your project storage. You can also do it in Scratch, and you probably don't want to do it in home because it's only the 25 gigabyte. but home is the only place that's backed up, and that means you can put your configuration files there. All of it is accessible by the batch system, though Scratch is only accessible while your node is only accessible while your job is running on a specific node. And the performance is high for the two first, and slightly less on the Scratch. That's a different system. The two first is running on our Lustre system, so the project storage and our home. And as default in the project storage, no one but your group can read stuff there, and in your home directory or on Scratch, it's only you by default. And you can use change mod or change group or ACL permissions to manage permissions there. And of course, on Scratch, it's not applicable because it's only the batch job that has access. So in short, use a storage project. You should choose a directory name when you apply for a storage project, or you will get the project ID. And in this case, we got the project ID. Remember, it's this here. And the location is always on the /pri/no backup/ the name you picked. And you need to create the subdirectory. So on Kebnekaise, we have a module system that are used to handle access. Most programs are accessed by loading them as a module first. So it is not that you can write, for instance, GrowMax. Nothing will happen when you do that until you have loaded the module, for instance. And the modules, they are used to set up the environment, that is the paths to executables, to libraries, etc., for some set of software packages. And it is a help to manage your shell environments. That is, it sets various shell environments, for instance, to where does it find the library files and things like this. Where does it find other? There will be a number of environment variable settings, and it's very practical because it creates and removes it dynamically without you having to do it by just loading this module. And another practical thing is that you also can have several versions of the program or package available, and you easily access it by just loading that version and then unload another one and things like this. And that is useful, for instance, if you have several compilers, which can otherwise be difficult to have on the same system in different versions. And modules are installed hierarchically, and that means that some of the modules will only be available after you have loaded, for instance, a specific compiler or MPI version. So there are several useful commands to the module system, and some of the important ones are to see which modules exist. And there is this one that is called module spider, or ML spider for short. I will show you what happens when I write that. Then it will show a list of all the many programs that exist here as software, or everything you can install, and there are very, very many of them. And you can exit that by just pressing Q. So what you would do if you just want to see if there are, for instance, any programs for any Python, then you would say ml spider Python. And then it lists which Python versions are installed. So you can see there's quite many of them here, both for Python 2 and Python 3. And it also gives some other information. And then say you wanted to load Python 396. Then we will do ml spider and then Python 396. And then it tells you that it also provides a number of extensions. That is things like Python packages that will be installed and accessible together with it. And it tells you another important thing, which is In order to load this module here, you also need to load this module first. So in this case, I would do ml to load, as I said. That is short for module load. And then I would take this GCC core 1120, and then I would take Python 396, and then I can load both of them at the same time. And then I would say ml to see what I have loaded. And you can see here it has loaded the GCC core, and together with that, it loads a number of other things. And then I also loaded the Python 396. In order to remove all of that, I could do ml purge or module purge. Then it now only has these so-called sticky modules left. And the sticky modules contain a number of environmental variables, and you want to keep those. So let's try look at FOSS. FOSS is, let's see, you can use MLAV also. That is also a good thing to look at. That is everything you are able to load directly given what is loaded now. And in this case, I haven't loaded anything, so it shows things that can be loaded directly. And that is a small number of software packages, and it is all the compiler tool chains, as they are called. And a compiler tool chain is a compiler. It is often also things like API libraries, and often also things like, for instance, a number of other scientific libraries. It can be CUDA, it can be many things. So let's try and look at FOSS CUDA 2020b. So I will do ml spider FOSS CUDA 2020b. I'm told I can load it directly. It says so here. If I didn't know which versions were of FOSS CUDA, I would just say ml spider FOSS CUDA, and then it says there are these different versions. Regardless, I will load it directly as I could, like that, and then I do ml, and you can see here it loaded a lot of things. And it loaded a GCC compiler. It loaded OpenMPI, and a BLAS, fast Fourier transformation, scalar pack, Apex, many things. And you can also use ml show on a module, and that will give you more information about this module. And what it gives you here is information about what other modules it would load, and where it is located. For instance, this is the location of the installation on this system. So, and as I mentioned here, compiler tool chains, there is a number of them here. And that is basically GCC or Intel combined with various libraries and CUDA. And you can look at each of them and see which ones contain what and what you want to load. But in the examples here, the first ones here, the simple ones, we will be using FOSS or FOSS CUDA, and there will be different modules loaded in the afternoon for the application examples. And let's assume that you're compiling something yourself. Then you might want to know how to link with the libraries. And an easy way of doing this is to use something called build-env. That is a module, and you can load it. There's a ml build-env. and it loaded that. I do ls. I wanted to do ml. You can see it loaded the build env. And the good thing is now when you say ml show build env, it will show you not just what it looks like when you're loading it, but also which other. It will show you how you can load various libraries, how you can link with them. So you can scroll down here, you can see there is a whole lot of things. But what you want to go down to is to find these here. And here it tells you, say you wanted to link to BLAS. And then it tells you that to link to BLAS, you can use -l open BLAS -lg Fortran. And it tells you how to link with LayPack, how to link with the Scalar pack, and things like this. Another thing that might even be easier is if you have loaded build env after you loaded the compiler toolchain, then you can use these environment variables to link with instead, but prefaced with a $sign, as I say here. So $libBLAS is the same as writing -l open BLAS -lg Fortran, for instance. And what you can also see here is that it tells you what is the name of the MPI-C compiler, what is the name of the Fortran compiler, what is the name, and so of regular compilers here. And this. So this is very useful if you are compiling yourself and linking with things. So let's move on to the batch system. And the batch system at SPC2N on Kebnekaise and also at many of the other systems that you might have access to in Sweden will be Slurm. And Slurm is an open source job scheduler, and it provides 3 key functions. So, I mean, it keeps track of the available system resources. It will enforce local system resource usage and job scheduling policies. It also manages a job queue, and it distributes the work across resources according to those policies. And if you have any larger jobs, parallel jobs, GPU jobs, anything, you have to run it through the batch system. And to do that, you also need to create and submit a Slurm submit file. And if you are Googling this online and indeed looking in our documentation, it varies a lot what people call it. Many will call it a Slurm submit file, some will call it a batch submit file, batch script, job script. All of these things are referring to the same thing. And there is a lot of guides and documentation on our website here. So what is it that these core hours are, and how do we handle accounting? And accounting does not mean that you pay for it with money, because if you are in Swedish academia or part of a project with a PI in Swedish academia, you do not pay to use it. But accounting is how much is your project accounted for, and it is used to find your priority when you are in the queue compared to the others who are also in the queue. So assume that you are asking for 1 core, and then you will get 1 core, and you will be accounted for 1 core hour. And a common amount of time you could have on a small project might be 5,000 core hours per month. And that meant that you could ask for, say, 10 cores in 10 hours or something. That would be 100 core hours. So you can calculate it that way. And if you're asking for 28 cores, then you would get still 28 cores. There's 28 cores on a node. If you're asking for more cores than there is on one of these nodes, or the Skylake nodes, then you would get a whole multiplum of 28 core hours. So that means that if you ask for 29 cores, you would actually get 2 times 28 cores, because as soon as you go over one node, you will get whole nodes accounted for, and also allocated to you. So this is a Skylake node used as an example. And if you were instead using Broadwell nodes, it would be the same, except it has a different amount of memory. And the large mem nodes is exactly the same, except that there are more cores, so you need to go up to one full node there before it starts going full nodes. And then we have the K80 nodes, that is the GPU nodes, and they have either one or there will be either one or two cards on each, except for a small number of nodes which has 4. So you can either ask for 1, 2, or 4. If you ask for 3, you will also get 4. And what we have is what we call GPU hours instead. And so that means that you will get accounted for a certain number of GPU hours. And one thing you should know, which I failed to say before, is that when you are asking for a project on Kebnekaise, you also need to specify which resources you want. And just the regular Kebnekaise resource will just give you access to the CPU nodes. And if you ask for the GPU partition as well, then you will also get access to the GPU nodes. And we have that for this project. And let's see if I can find this here. There it was. So as you can see here, this is the regular CPU partition. And there we have 20,000 CPU hours per month. And on the GPU, we have 10,000, and it calls it CPU hours because, well, it's using the wrong word, but it doesn't work that way. You only have to look on the super page to see what it translates it to. But in any way, it will be a number of GPU hours that you can use, and this will use up 2 of them if you ran for 1 hour on full K80. And the V100 is exactly the same thing. The only difference is that these K80s have 2 onboard compute engines, whereas the V100 has only 1 onboard engine. But otherwise, you can see here how much you are accounted for if you use 1 of them or 2 of them or more of them. The A100 we have decided are slightly more expensive to use because there are fewer of them, but also because they are faster. So we have tried to weigh it compared to how much usage you can get from them compared to the that number of CPU hours instead. So what are some useful commands to this batch system? Well, if you have written your job script, then you would submit it with sbatch and the name of the job script. And you could call the job script anything you wanted. It doesn't matter, just as long as you can recognize it. It's very common to use a suffix of .sh or .batch or .sbatch, and that can make it easier for you to see what batch scripts you have. So that is not a bad idea to do. So we'll use that to submit it. And when you submit, then you will also get a job ID. And I will show you that in a moment. To get a list of the jobs you currently have, you use SQ, or better SQ minus U and your username, because then it only lists your names and your jobs, and it could be a lot of jobs that people are running. So that might also be a good idea. And with srun, you can use that and give commands directly to the job instead of putting it in a job script. That is usually not recommended because then it's difficult to be sure that you're doing the same thing next time. I mean, if you have a job script, you can see what you did last time, and if you want to do the same. To check on a specific job, use scontrol show job and the job ID. And if you want to delete a job, you can do that with scancel and the job ID. And if you want to delete all your own jobs, use scancel -u and your username. And there are ways to get more detailed info about a job ID. And a more graphical way of doing that is to use the command job -usage and the job ID. If you do that, then you will get a URL that you can paste into a browser, and then you can look at the memory usage and other things like that. And you can, of course, use man sbatch, man srun, etc. to get more information. So the output and the errors from a job that you have ran, they'll usually go to slurm minus the job ID.out. You could look at it with any of the editors, or you could look at it with cat or less, which just throws the content of the file to the window that you're looking in. And you can split up output and error files if you give flags in the submit script. Which is sbatch -error equals whatever you want to call it, and or minus output and what you want to call that. And this is an example. You can call it what you want, but I suggest you put the %j in the name for the simple reason that this is an environmental variable that will contain the job ID, and that means that if you run it several times, you will then get new output for each of them instead of overwriting the one that you had. So this might be a good idea to do that. And if you want to use the various parts of Kebnekaise specifically, there is a fat nodes, that is also the ones with lots of memory. You do that by adding sbatch -p large mem. Remember, it's a separate resource you need to apply for, and we don't have that in the Quartz project. If you run on only the Broadwell nodes, only the Skylakes, or only the AMD Zen 3 CPUs, which can be necessary if you are doing things like benchmarking, then you can add constraints, and you can see here how you do that. And if you want to use the GPU nodes, again, separate resource, which you apply for through Super, and we have done that for the course. Then you do sbatch. It's important to have this hashtag, and then sbatch, which must be in capital letters. -gres equals GPU : the type of card, that is K80, B100, or A100, and :x, where that is the number of these cards, and that can be 1, 2, or 4. The 4 is only for the K80s. So in this case, it would be 1 or 2. If you're using the A100 nodes, you also need to add the partition, just like this. And in order to find the correct modules and compilers and things like this, you may want to log in to one of these login nodes. This with ThinLink, or this with regular SSH. There is a web page about how to use Kebnekaise where you can find this and more info. So let's look at an example here. And this is a simple example. There is a serial job on Kebnekaise with the compiler toolchain FOSS. And first, this line here you see looks like some sort of incantation. It tells the batch system that you are running it in the bash shell. And that has to be there always, because the bash shell is the only one that's completely compatible with the batch system. So it's important to add that always. Just put it there and don't think about it any more than that. Then you need to add the project ID. And in this case, it is this here. And you change that after the course to whatever your own project ID is. In this example, it's a serial example, so we're asking for 1 core. And we're wanting a wall time of 5 minutes. This is hours, minutes, and seconds. And 7 days is the longest you can run a job because, well, there are several reasons. One of them is that we need to be able to do maintenance with regular interval. So we can't have job running for too long. But another thing is that the longer your job runs, the more likely it will be that something will happen that means that it crashes. And if you don't do checkpointing or something, then you may lose a lot of work. So that is a danger if you're running very long jobs. After this, you want to load any modules, and it's also a good idea to purge modules before loading new ones, and that is mainly if you, for instance, have something put in your login script that loads modules. Many people do that, which they shouldn't. But if you put ml purge, then you're sure it removes all other modules, and then you load the module that you actually need. And in this case, it's Frost/2021b. And then you start your program. And in this case, it's just some serial program that's compiled, and you're using / to say it's in this directory and then the name of it. And then you submit it with sbatch JavaScript.
One thing is one common misunderstanding is that this ML purge is not a module, right? It's a yes,
no,
as
it's a
Birgitte
command.
said, it's a
it's
way
a command.
yes,
Yeah.
it's a command.
Yeah, ML is short for module. So think of it as module purge. So it purge the modules. An MPI program you would run, for instance. So this is an example of a parallel example. And this is just a MPI C program that does hello world, just to have some example. And then when you run it, in this case, you want to run 14 tasks, and the default is that it will run 1 task per core. So this will be the same as that, but you can change the number of tasks with the C command I just mentioned. And they will have to also use srun to run a parallel program. So srun will run it on 14 cores, so it will run 14 tasks. And this is how the output will look. And if you run it several times, start several jobs and look at each of them, you will see that the order is random because it is different which one will answer first of them. So the order will be random. It's also possible to run more than 1 serial job in the same submit file. And to do that, you will need to use srun, even if it's serial jobs. But you'd simply put 1 for each of the serial jobs, and it's important to put and after. And it's important to put wait at the end, because that means it waits for the last one to finish before the job completes, as long as it can run within this time. And you ask for the number of cores that you will have jobs. If you want to run them sequentially, and let's assume it's also parallel jobs, then you also need to ask for enough tasks, and you need to ask for enough time that all jobs will complete. Since they are running sequentially, then it needs to be enough time that all of them together will finish. And since you are running them, since you are running them sequentially, you don't need to ask for more than enough cores than what is needed for the one that needs most, because they are doing it one at a time, so they're not running at the same time. If you're running at the same time, on the other hand, then the number needs to be the same as all of them put together. So, because they will all run at the same time, so there needs to be enough cores for that. And in this case, they will run at the same time. So the time you ask for should be the time it takes for the longest one to complete. And again, put the and put the wait. And put srun. And in this case, you will also need the bind to cores, since there will otherwise be problems when you're running at the same time. So what if you had a GPU job? And in this case, you are asking for two V100 jobs. And as I showed you before, this is the command you're using to ask for the V100 cards. And to run a CUDA program, you would load FOSS-CUDA. And in this case, it should have been 2020A, because 2021B is no longer available. Sorry, that needs to be 2028. And then let's do one more example with A100 cards. And here you both ask for the partition and also for the A100 cards themselves. And then you will also have to load this module here to run a CUDA program. And as you can see, it's different to the one for the V100. And that's simply because the modules are different on these A100 nodes, and you can see that by logging in to the login node there. So I have gathered the important information here. There's a project ID and how you write it in your batch job. And there are some nodes reserved for the course. And that is because otherwise it may take a long time to get to run if many people are using the system. And that means that you can add these reservations. If you're running a CPU job, you add this one. If you're running a GPU job, you can add that one. You can also just try to run it without it, because I don't think there are too many that are running something on the system right now. And then there's the storage project also listed again. If you have any questions, you can ask me, you can ask it on the Q&A document, ask Pedro, or look in the documentation or send support questions to us. I will just show you now how to get the exercises and a quick look at how you find the exercises and other things, and also how you start a job and things like that. I will just do that very quickly because you should have lunch in a moment. So here is the GitHub page again. And on this GitHub page, you can see, you can find it up here. There is a green button that says code. Click that one. And then you want to clone, and it must be the HTTPS one, because to use the SSH one requires that you have read-write access to this specific GitHub repo. And if you don't have that, you cannot use that. So you have to use HTTPS. So copy that, for instance, by clicking here. And now let's go to this. Just make this a bit larger. But good. As you can see, I'm here in the directory I created under the project directory, and I'm going to write git clone, and then this URL for the repo that I just copied, and then it will clone the content. It will take a small amount of time. Okay, I will do ls, and you can see it now created the directory. I will go into this directory, and under that, I'll just move it up a little bit. You can see there are a subdirectory called hands-on, and there's one called slides. And there's also a text called readme, a file called readme.md. It's this one that it shows here. So let's go to the hands-ons. And there is one called 3.usage. Let's go into that since it's session 3 using the system. And here you can see there is a list of different programs and submit scripts. And there is also a README file. If you are looking at it on the web, like this here, then I would suggest you click the file that ends in MD, because that will make a somewhat nicely formatted one. If you're reading it on this terminal here, then the .text one is easier to read, because then you avoid the formatting stuff for the .md file. But the README file will contain some information about how to load and unload modules, and also a list of the jobs and what they do, and how to submit a job, how to see the status of it. So it's a refresher on that, and how you compile programs. All of that you can find in the README file. And if you go in, sorry, if you instead go to the exercises MD, then there are the actual exercises. So what I guess you could do is that you could open both the README file here and also the exercise itself, so that you can check if there's anything you want to check. Anyway, the exercises are pretty simple, but that's first the one that you should create a directory for yourself after you have cloned this repo. And then some exercises on loading modules, and some exercises on trying to compile and run things like this. And again, there are descriptions in the README file of how to do that. And then comes an exercise about how to do batch jobs and stuff, and submit these batch scripts. I think that we should take the lunch break. Let's see. Yes. So let's do the lunch break and come back at 1. And then you will do the hands-on. But just before we do that, I will just quickly maybe show you how to submit one of the job scripts and things like that, and check on it. But I think we should do the lunch break first, so it doesn't get too much overtime session. So I will probably share my screen again. Let's see. That one. Yes. Okay. So I showed you where the exercises were, and you could find them here on the GitHub. And I'm assuming you will now have cloned this Git repository So they are on your space on the project storage. And that is where I have it here in my example here. So as you can see here, I went to the project storage. I created my subdirectory, named my username. I cloned the Git repo, and then I went into the Git repo that was cloned, which was called intro-course. I went into hands-ons, and it went into the subdirectory 3.usage. And in this one, you have this many different files here. We have the README files with some instructions and help to how to compile things and how to load modules and which ones. And you have the exercise ones for the actual exercises. The .md files are good to use if you're watching it on the web browser or in some program that you have downloaded for showing files, such as MD files. Otherwise, I would look at the .text file. They have the same content, it's just some formatting issues. So let's try look at the first simple example. I have one that's called simple.sh here. And I'm going to open that here. So this looks like this. And here you can see it has the project ID, asking for 1 core, 1 minute. I'm loading the FOSS 2021B module, and I'm running the program hello. So I would like to do that. And in order to do that, I first need to compile it. It's this one, hello.c. And in order to compile it, I need to load a C compiler. And I'm going to use FOSS. So just to recap, I'm going to do module spider FOSS, because that tells me which modules are on the FOSS, and I'm going to go with this one. So I will say module spider on that one. And then it says this module can be loaded directly. So I will load it. And then it told me I had something first, so I will purge everything just to make sure it doesn't go bad. Then I will reload. So I say ML, and here you can see what it has loaded. And I am going to say, I'm going to load build-in as well. That. And then I will say ML show build-in. You don't need to do this. I'm just doing it to show you. Because then I'm going to use this to find out what is the name of the compiler. And here I check, I find that it is GCC. I probably already knew this, but let's compile it. So I say GCC hello.c. And if I just do this, it will generate a binary called a.out. I would like it to be called hello because I used that in my batch script. And because if it just is called a.out for all of them, then they will be overwritten when I compile different ones. I will do this, and the -o hello means I want the output, the binary, to be named as hello. Compiled very quickly. And because it's a short program, I will show you it can run on the login node. Just says hello world. But now I'm going to submit it instead. So I will, it is called simple.sh. So I say sbatch simple.sh. And you can see here when I submitted it, it tells me a job ID. Most likely this has already run, but let's try and see. Yes, I don't have anything there. So I will quickly submit it again and look at the queue. Now you can see I have a job with this job ID here. It is named single because it's running in the single partition. It's named simple because if you don't name the job, it will just have the name of your submit script. It's me, user. It has the status R for running. It has at this time run for 1 second and it's running on BCN 1512. So let's see what happened. And you can see this was the job ID. And I got a output file that has this name. Let us look at it with cat. And cat contains first this part, which is because I ran ML purge, and you can just ignore it. And then it has the actual output, which is hello world. So. And let's try running something else. We can try the hello world as an MPI program. So I now need to compile MPI hello C here. And it's MPI CC is the name of the MPI compiler. And because I do it this way, I am naming it MPI underscore hello. Ran. Oh, it compiled, sorry. Let's look at the script here. You can see here how it looks, and I would like to run it. Dispatch. Hello. Like that. And it's probably already either running or have run. It's currently running. It's still running. And now it's completing. And now it has run. And you can see here it ran and created output for each of the processors. So you can also use S-control show job and then the job ID. But when it has run, there is little to see in it, except that you can see that it has completed. But if it hadn't, then there would be an estimated start time here, which could change. And depending on other people's jobs, if they finish earlier, or if someone with higher priority is submitting jobs. But this is quite useful info. It tells you the working directory, where you have it. It tells you where it outputs things. And you can see the node list, what it was running on. And it can also see here, it tells you it's completed. It tells you how long did it run for 12 seconds and things like this. So, and you can also then give the job usage. And now I need the ID again. And as you can see here, then you are getting a URL. So I copied it and let's then open it. And it didn't copy on anything for some reason. So let's do this instead. See, and this is the info you would get. But since it ran for very short, it doesn't have much of any info here. But if it was a longer job, it would have more information here. So this is useful if you are if you have some job that is generating a lot of information, a lot of output. You can see, for instance, how much memory it used before it crashed, if that is the case, if it crashed. So you could at least see that it uses more than some amount of memory. I would like to do one more thing before I let you look at this, and that is I would look at this one here for the A100, and you can submit it from this node here. It will know to go to the right partition, the right nodes. But if you wanted to see which module it is you need to use, I will just show this one. Yeah. You can see here it's using a module called CUDA 1170. And I'm going to try and log in to Kebnekaise. There. And then I can do ML Spider CUDA, for instance. And this is the login node for the AMD nodes, including the NVIDIA GPUs A100, because those are located on AMD nodes. So if you are on this node here, and when you have logged in with ThinLink to the regular Kebnekaise login node, you can open the terminal window, a shell or something, and then just do SSH Kebnekaise -AMD to go there and see what is the name of the modules if you want to run on that. But I'm going to log out again. But I think that is what I wanted to say, and then I think that I will let you try and run some of the exercises and see how that goes.